recording today because we try to be smart. Okay, so if we look at today's challenge problem, so in this week's lab we are starting to talk, or this week's, excuse me, or today's activity, we are beginning to look at how these these three-dimensional structures that we've talked about in terms of the Lewis structures impact our molecules as they interact in terms of liquids. So when they're in their liquid state, how is these intermolecular forces which are generated from their three-dimensional shapes, how is that impacting the properties we see in our liquids? Right? So for the challenge problem, now that I finally got there, we can see, blow it up a little bit so it's not minuscule, that we want to put these compounds in order of increasing boiling point. So if we think about what happens when we boil something, just as an aside, if we look at, we have a container on the stove, right? We fill that with, say, water, and we heat it up. What we're doing when we boil the water is we are taking these water molecules and they are escaping out of our solution. And their ability to escape is going to be directly related to how tightly they're held together, right? So therefore, if we increase the intermolecular force, we should see a corresponding increase in boiling point. So something with a larger intermolecular force is going to have a higher boiling point. So then we have to arrange these four molecules in terms of their intermolecular forces, right? So we have to figure out which intermolecular force is present in each one, and then we can arrange them. And I'm going to well, let's look at them. So we're going to draw the Lewis structure for each one. So if we look at CH4, it has this Lewis structure. CH3, CH2, Cl has this Lewis structure. CH3, CH3 has this Lewis structure. And finally, CH3, CH2, C, or OH, excuse me, has this Lewis structure. Right? So then if we look at the types of intermolecular bonds that are present in the methane, the CH4, right? Because this is symmetric, there is no difference in electronegativity or very little difference in electronegativity between the carbon and the hydrogen. This is going to be non-polar, and it has a tetrahedral, just to review, shape, right? And which means that this is going to have only dispersion, which I misspelled. London dispersion forces. Right? If we come over to the CH3, CH2, Cl, now if we divide this molecule in half here, right, assuming it's at the center, this side doesn't look like this side anymore. So even though around that molecule, it is still, if we make this the center of the molecule, it's still tetrahedral, it is now polar. So this is going to have this both London dispersion and dipole front.
Can we talk about how the Alakir warriors in Skyrim just Morgan Freeman's character
I'm sorry, I didn't quite hear that.
from Robin Hood?
One more time.
Plagiarism or racist?
I think it's an accident.
All of the above.
All right.
But they didn't like try to hide the fact that they were just ripping straight from this. They have
Maybe. Okay. All right. So if we come back to this molecule, the next one, the CH3,
the same sword. Literally everything about the costume design is
we see that again. If we look at each one of those, because there's very little difference in electronegativity between this carbon, between the two carbons and this carbon, right? They are the same and they have the same things around them. This would also be a nonpolar molecule, which means the only thing it has is London dispersion forces as well. And then finally down here at this one, again, if we separate this molecule through the center, this side doesn't look like this side, so it becomes polar. And it has dipole-dipole, but now we have this hydrogen directly bound to the oxygen, so this one has hydrogen bonding as its strongest. So that means that the stronger the interaction, the higher the boiling point. So this one being the strongest would have the highest boiling point. So if we arrange these then with increasing order of boiling point, right, we would have CH3, CH2, OH as being the largest. The one with the dipole, CH3, CH2, Cl as being the next. Now we have to look between these two that only have London dispersion, right? And if we think about London dispersion as this temporary dipole, the more that we can get these two molecules to overlap another molecule of the same type, the stronger that interaction is going to be. So we can think about these in terms of stackability, right? So this one, because it is longer and has more mass, is going to have a larger London dispersion force than the methanol or methane because it's got a smaller mass, right? So if we come down here then to finish this out, this would be CH3, CH3, and our lowest one would be CH4, right? So if this would be in order of increasing IMF and the boiling point, which should not be B, it's BP. All right. Questions on that? So again, we're going all the way back to these Lewis structures to determine the shapes, whether they're polar or nonpolar. That's going to allow us to determine the intermolecular forces that are present, and that's in a lot of cases going to be dependent on how strong these physical properties are, whether we talk about vapor pressure or viscosity. All of that is dependent on the intermolecular force that is present. And in some ways, this is also going to play to the part when we talk about the surface tension. All of these intermolecular forces are really going to determine how tightly these are bound together, which is going to determine how things are held, which is going to affect, as long as we understand what the intermolecular force that we're talking about, or the property that we're talking about, how that's affected by how tightly those are, we can do those orderings. Any questions about that or anything else before we break into our groups to start talking about to start doing the activity? Any questions? Mhm.